Hello, this is Mr. Ralph coming to you from home. If you guys hear sound in the background, that would be my sons. Today we're going to start talking about a concept which we know, at least in part, which is called friction. If my pad would actually write for me. All right, so to talk about friction, I want to talk about a very particular situation. Let's say, for example, it's a very common case. We have a rough surface. And on that rough surface, we have a box. And we know that when we have an object sitting on a rough surface, I know there's a gap here. There's not really supposed to be a gap there, but if I were to zoom in on this box resting on this surface, what I would see is something that looks like this. I'd see the bottom of the box is super rough, like this. And it's got these highs and lows, and the surface itself is also very rough, and there are some places in which the roughness of the surface interacts with the roughness of the box right at these junctions. Okay, well, maybe not use red, let's use black, so that's a little bit more obvious. So here's an interaction, here's an interaction, here's a little bit of an interaction, here's an interaction. So if I wanted to say, for example, to push this box in this direction, I'm going to have to overcome all these little microscopic interactions that are occurring between the atoms on the bottom side of this book and the atoms on the top side of this surface. So, well, let's talk about what that actually means. So, I want us to imagine if the box is sitting on the ground, there are a couple of things that we need to account for. First off, if we were to draw a free body diagram on the box, we know that there will be a force pulling that box down because it is on Earth. We would call that force its weight. So we can use the symbol W to represent its weight, or we could express what's happening to the box as the force of gravity, which is F sub G. Alternatively, we could express the force acting on that object as the mass of the box times the gravitational acceleration that box is experiencing. So these are three different ways to express what's happening to the box as it's being pulled downwards. Now, looking at this force diagram as we see it currently, what we would glean from this is that with no other forces, this box would be accelerating towards the center of the Earth with this acceleration, g, which is 9.8 meters per second squared. Clearly, we don't want that to be the case. Let's just assume that the velocity of the box currently is 0. It is not moving. That tells us some things about what's happening to the box. First off, we can definitely say that the force net on the box is also equal to 0, which tells us some more. Because if the force net is 0, the force in all directions have to be balanced, which means we need some more forces. So first off, if I've got a force pulling us down, that means that we also have a force pushing me back up. And that force is equal and opposite to the weight of the object. We would call that force the normal force. So F sub n is one way that we can talk about it. We could also talk about it as, let me use the undo feature. We could also talk about it just as a big N. Or another way that we could talk about it is we could use a little n. So there are a couple of different ways to express that normal force. F sub n, big N, and little n. I'm going to go ahead and use big N to express the normal force. We know they're both equal and opposite again because the object's not moving and its force net is 0. Also in this example, I want us to consider if we were to start to push this object in this direction. Of course, we would be applying a force, so we'll call that the applied force, F-A-P-P. Knowing what we know, the force net on this object, though, is 0 because it is not moving. That means that I have some force of friction acting in the opposite direction that's equal and opposite to the applied force. We're going to call that static friction. If that object is experiencing static friction, it is always going to be equal and opposite to the applied force. Now hold on a second. We know that we can push objects hard enough to where they start moving. But if they've started moving, that means that we're dealing with some other type of friction, because static friction that you see here literally means, the word static literally means not moving. Okay, well then let's draw ourselves a second diagram. All right, well here's our second diagram. Same box, same surface. Here's the box, except this time my box is going to be moving in this direction. And we can say that that velocity value is no longer 0. Okay, I'm not going to say what it is because it's probably going to be some sort of constant or non-constant value. Could be accelerating, could be moving at constant speed. And as soon as that object starts moving, we know that the forces on this object could be balanced. Well, as soon as it starts to move, it's going to accelerate. So let's just consider that case for a second. That means that we've got gravity, we've got the normal force, we've got the force applied in this direction, and then in the backwards direction, we're going to have a smaller force, at least while it's accelerating, and that force we're going to call kinetic friction, F sub K. Okay. So let's consider those two diagrams just for a second. And of course, this is not the same size as that, but this is the same size as that. Okay, and you can see those two diagrams and make a relationship between the two. Well, the ways in which these two things are related or interrelated is like this. How the heck do we actually determine what the friction is in each of these cases? Well, from previous videos that I've shown you, we should have seen that the force of static friction is equal to some weird little character that looks like this. Mu sub s times the normal force. Or put in a different way, because we know that the normal force is equal and opposite to the force of gravity. Another way of saying that is that it is equal to, or sorry, I should say less than or equal to mu sub s times not n, but mg, the mass of the object times the acceleration due to gravity. And keep in mind, again, that g, not q, g is equal to 9.8 meters per second squared. Okay, just keep that in mind. So this is the formula that tells us the static friction that's working on the object, how big this force is. And note that that is only related to the normal force, how hard the surface that it's sitting on is pressing into the microscopic little pieces of this box. Okay. Also note that it is less than or equal to that normal force. It can't ever get any bigger than the applied force, is what we're trying to say. It'll grow to a certain size, and then it'll stop growing. So all of a sudden it'll break, which then gives rise to kinetic friction. The object is actually moving forward now at this point. And so the force of kinetic friction is actually equal to, it's not greater than or equal to, it is a constant number. It is equal to mu sub k. Oops, I brought up my brush menu. Let me get rid of that. You didn't see that on your screen, but I did. Mu sub k times, again, the normal force, which we then know, if we break that down into a more usable fashion, is mu sub k times mg. Okay, so these are the two formulas that we really want to consider when we are talking about these two different situations on the same box. All right. Now we got to do some math, because we want to put all of this stuff into practice somehow. So I'm going to go ahead and I'm going to erase some of this stuff and add some additional things. So I'm just going to go ahead and let's just nuke it all. Let's create a completely new document. File, new. All right, I'm still not very good at this, so I apologize. I just wiped it out. It's still there. We can go back to it. We can refer back to it and see it. But we're going to wipe it out just for a second. So again, we're going to start out with our object. We understand that it is a box that is sitting on a rough surface. It is experiencing forces. Those forces are gravity downwards. So we're going to call that mg in this case, just to make it a little bit more understandable. We're going to call the force going upwards, we're going to call that big N. We're going to call the force going to the side F applied. Come on, pen, wake up. And then we're going to call the force going in the opposite direction. And again, these aren't to scale, the force of friction. Now, we're not going to give it an S or a K just now, because what we want to do now, understanding that our different formulas are F sub S is less than or equal to, mu sub S mg, and the force of kinetic friction is equal to mu sub K mg. What we want to do with this information is we want to build for ourselves just a little table to understand exactly what these forces mean. Now, I have included this same table in the problems that I have assigned to you. So now is your opportunity to work through this with me so that you have that table and kind of understand what's going on. So I'm going to do the same table, and then you're going to make some conclusions based off of it as we watch through this video. Okay, well, if that's the case, we kind of need to make sure that, our object, that is not what I wanted. I wanted to be able to write, and that thing did not do what I wanted to do. We want to make sure that our object has 5 kilograms of mass, because that's going to allow us to determine some different things about the object, the forces in particular. All I needed was that 5 kilograms, because now I got a mass, I've got the acceleration due to gravity, and now I want to talk about some different coefficients. So let's say, for example, mu sub S in this case is equal to 0.6. Now notice, there are no units. Mu sub S is a ratio. Mu is a ratio. Basically, it's saying if I give you this force, I will get this force out. And so there are no units that are associated with this. For the surface that this is sitting on, mu sub K is 0.2. And what you will universally find is that mu sub S is going to be the bigger of these two. It is harder to get the object started in its movement than it is to keep it moving, is basically what this is saying. Mu sub K is always going to be the smaller of the two. Sometimes they'll be very similar, but mu sub K is always going to be the smaller of the two. Okay. Well, let's actually figure out what these breakpoints would be then. Let's figure out what the maximum value of mu sub S is. Let's figure out what friction sub S, F sub S, and F sub K are in each of these cases at its maximum and what it's equal to. Okay, well, that means, let me do this in red so it's a little bit more easy to see. Well, this is going to be equal to, let's substitute our numbers. Well, mu sub S is 0.6 times 5 kilograms times 9.8 meters per second squared. Okay? And if I do that math, let's figure out what that is. That becomes 29.4 newtons. That's 29.4 newtons. If I do that same math down here, this is going to be instead 0.2 right here. Mu sub K is 0.2. So this is going to be 0.2 times 5 kilograms times 9.8 meters per second squared. Okay. And that is equal to, I don't even know. Let's see, it would be equal to, 0.2 and 5 are going to basically cancel each other out because that's the same thing as saying 1/5. So then this becomes 9.8 newtons. All right, so we've solved those two different pieces real quick. I'm going to go ahead and just put these underneath. So this is 29.4 newtons, just for quick reference. This is 9.8 newtons, just for quick reference. And then I'm going to go ahead and create for myself a little space right there so I can actually do some things. Boom. Yeah, do that. Don't know what it's trying to do. Okay. All right, so now what we want to do is we want to start building this table of forces. So what I want us to imagine is, oops, I'm on the wrong tool here. Hold on. Still pretty new at this. I want us to imagine we have a table. You should have a table in your notes. The document that I've provided you, and it's going to look very much the same. All right, so in this table, we're going to have our different forces. We're going to have the applied force, FAPP. We're going to have the static friction as another column. We are going to have the kinetic friction as a third column, and we are going to have the net force as our final column. Okay, so in your document, what you're going to see is that we want to consider what's going to happen if the applied force is 0 newtons. Actually, I'm going to get rid of that. That's kind of garbage looking. Oops. The applied force is 0. I'm not going to use my units here because I think it'll be easier to see without units. If it's at 0 newtons, if it's at 10 newtons, if it's at 29.4 newtons, and finally if it's at 30 newtons, what all these forces are going to look like. Okay, so first off, if we're applying 0 force on this side of the object, logically we could say to ourselves, well, there should be no force on this side of the object because friction only counteracts motion. And if we're applying a force over here, only when we're applying a force over here are we going to see a force over here. So that means that, well, there can't be kinetic friction because the object's not moving. And since the object's not moving, there is 0 force, which means then that there has to be 0 static friction in order to make everything work. If that's the case, then all of these are zeros. So if I apply no force, there is no static friction, there is no kinetic friction, there is no force net. Going back over here, look, static friction is less than or equal to this top value. Okay, well, what if I step up the force? We've all been in a situation where we've been pushing a box really hard, and it's on a rough surface, and it doesn't move. Well, is 10 newtons enough to make it move? Well, look at our top value here. Our top value is 29.4. So that means the object's not going to be moving. Okay, but I'm applying a force. That means that static friction suddenly exists. There is a force. If I'm applying a force this way, there has to be a force being applied back at me. But I know that if I'm applying that force and the object's not moving, that the net force on the object also has to be 0. Now here's where it gets a little bit tricky, because you would think that then if there is static friction right here, and I didn't just draw a 0, that was actually supposed to be a circle. Let me draw a box. There. This number right here, whatever it is, should probably be this, right? Because it means that since it exists, it's going to push back with the full force. Well, hold on. If I make that 29.4, all of a sudden 29.4 subtracted from 10 is not 0. I can't have, basically what you're saying in that case is if I'm applying a force forward, the object is going to push back against me with more force than I pushed it. No one has ever experienced anything like that. That just doesn't exist in nature. And so as a result, what you're actually going to experience is that since the force net is 0, this is also 10. And that makes perfect sense once we really think about it. What happens at 29.94, which is exactly the value right here? Well, if I put in 29.94, that means this is going to max out this static friction value. 29.94. But I haven't surpassed it. So the object's not moving yet. Force net is 0 because there is no kinetic friction because the object is not yet moving. Well, what happens at 30? Well, clearly 30 is bigger than 29.94. And so now we've surpassed this threshold at which friction, the static friction, is pushing against us with a significant enough force to prevent us from moving. Now we're moving. And since we're moving, static friction goes away. This number doesn't mean anything anymore. Static friction now becomes 0. All the time before, when kinetic friction wasn't there because the object wasn't moving. Well, now static friction is 0 because the object is moving. Well, that means that kinetic friction is always the same value as long as the object's moving. So now this is 9.8. Okay. But wait. Force net, as we know, is the sum of all forces. Well, to be a little bit more clear, I should probably put a negative sign out in front of these. So it's clearer. That's a negative and this is a negative. Because if I add 30 to negative 9.8, what I'm going to get then is 20.2 newtons. Oops, that's not a 2. That's newtons. 20.2 newtons of net force. All of a sudden, we should see now that this object right here is going to start to accelerate. Well, maybe we should ask ourselves, how fast is it going to accelerate? Sorry, my dogs are about to bark. Hold on, let me pause this video real quick. Okay, well, if we wanted to figure out what the actual acceleration of the object is, that's actually pretty easy because it's just Newton's second law. F net, in every case, is just equal to the mass times the acceleration of the object. We have the mass. We have the ability then we have the F net. We have the ability to solve for that acceleration. We know that F net in this case, when the object starts moving in this last column here, that's going to be 20.2. That the mass of the object is 5 kilograms. And then we've got our acceleration value. So basically, I just got to divide 20.2 by 5. Okay, so acceleration then equals 20.2 divided by 5. That's going to be right around 4. Hold on, let me actually get my calculator out real quick.